All right, well, hey, welcome to week 2 of Math 104, good old trig class. Today's plan is basically to pick up where we left off last time. Last time I introduced you to the trig functions and saw them as ratios of sides of triangles. Well, we're just gonna kind of keep going along with those. So that's my plan for today. But before I do that, I want to open it up to you guys. Are there any questions about any of the homeworks or anything else we've talked about up to this point that you'd like to discuss for a little bit?
I guess I had one more question on the homework if no one has a question.
Sure, which one, Danielle?
It was on the not the video. Sorry, I'm trying to pull it up on my other computer. Not the video assignment, but the other one. I think it was
Okay.
question 4. I didn't get that one.
Okay, let me just put that down on the list here.
So 7.1 practice question 4.
Okay, cool. Thanks. Any others for folks? You can throw them into the chat box if you think of them. All right, well then, let's go take a look at that one from 7.1 practice. So let me go ahead and share my screen. We'll go take a look at it. All right, so hopefully everybody can see it here. So number 4 says, we have a sector of a circle that has a central angle of 135 degrees. Find the area of the sector if the radius of the circle is 20 centimeters. All right, so they just gave us an angle and they gave us a radius. And it turns out that that's enough to find our area because we have a nice little formula that relates area with angles and radii and all that. So let me go ahead and jump to a whiteboard here. And we'll work this guy out. So the formula that we developed for the area of a sector of circle is 1/2 r squared theta. So this is the old, we've got a slice of pizza with a radius of r, angle of theta, and then area, A is going to be the area of it. All right, so we were told that theta was 135 degrees and r equals 20 centimeters. So notice that that's going to be enough, right? To get area, we just need to know r and theta, and we've got r and theta. However, there is one slight issue here. What do we have to worry about here before we just start plugging numbers in? Anybody know what we need to do? You can throw it into the chat box, yell it out.
Do you have to convert degrees to radians?
That is exactly what we have to do, right? This one, this theta, must be in radians. Otherwise, this formula is not going to work because it was developed that way. So in general, and the same thing is true for the S equals R theta formula. That's another one where theta needs to be in radians. So I hate to tell you this because I know you don't like hearing it, but your default should be radians. We need to train ourselves so that always we just are immediately thinking angles and radians, angles and radians, angles and radians, unless otherwise told, okay? Because radians are the default for a lot of them. All right, well, that means that we have to change that 135 degrees into radians. Well, the way we're going to do that, of course, is by multiplying by the conversion factor, which is pi over 180. So this is going to give us 135 pi over 180. And I'm pretty sure we can reduce that I think that ends up being 3/4 pi if we divide top and bottom by 45. But now that I've got that theta in radians, I can jump straight into my area formula. So the area is going to be 1/2 times our radius squared. So 1/2 times 20 squared times our theta. So 3 pi over 4. I think that gives us 150 pi. No, that is not correct. Hold on. Yeah, 20 squared is 400, 100, 300. Yeah, so 150 pi, which we can use our calculator to get a decimal approximation. And let's see what that is. My trusty black box says that that's around 471.24. And I'm going to be good about this. I'm going to put units on this. That's my science side showing. But we're going to do 471.24 square centimeters because our units were for length were centimeters. So we got a nice little formula. The kicker though is if your angle is not in degree or not in radians, you got to make it radians because this formula only works in radians.
Perfect. Thank you so much.
All right, you're welcome, Danielle. All right, so any others come up while we were doing that one? No? All right, well then I'm going to take your silence as everything is going fine with the homework. All right, that's going to be my default when it comes to homework is in the absence of questions or comments.
I got one.
Okay, go for it, Diego.
So for the video assignment,
Sure.
7.1, question 13,
Okay,
last one.
sure. Let me go ahead and pull that one up and we can take a look at that too. All right. So let's just backtrack there. 7.1 video. And number 13, the last one. All right, so find the distance that the Earth travels in one day in its path around the sun. Assume that a year has 365 days and that the path of the Earth around the sun is a circle of radius 93 million miles. Then round your answer to one decimal place, which is 100,000. Okay, just a couple of real quick things. Assume the year is 365 days. It's not. It's a little bit more than 365 days. And then the path around the Earth around the sun is a circle. It's not. It's actually an ellipse. And with a radius of 93 million miles. Again, not the radius, but we'll go with these numbers because it'll make it a little bit easier to approximate this distance. All right, so we just want to know how far it goes in one day. So let me share my whiteboard again. Let's clear all this. And so here's the picture. All right, so here's the sun. The Earth is going around it in a circle. This is definitely not to scale, and it's definitely not a circle. So we got the Earth cruising around it, right? And we know that it takes 365 days to go all the way around, but we want to know how far it goes in one day. All right, so if this is the Earth going around the sun in one day, it's going to move a little bit. I'm exaggerating it again, right? But we're going to go a certain distance in one day. And so the question is, what is that distance? All right, well, here's how I think about it. I'm going to think about this entire circle. Can I figure out the length of that total path? Can I find the total distance around that circle?
2 pi.
Okay, so 2 pi is the angle that we go through.
Oh,
But if I want that total distance, what do I do with that 2 pi? And I'll give you a hint. You don't even actually have to know anything about the angle. You can just go back to some formulas you learned when you were, at some younger point. It's just the circumference of the circle, which is 2 pi r, which if you think about how we defined arc length was r times theta. But if we do one circle, then it's a 2 pi. So this I can calculate pretty easily, right? It's going to be 2 pi times 93 million miles, which is whatever it happens to be, but let's see what it is. So 2 pi times 93. So that's 584.336 million miles. So just think about that for a second. That the Earth, as it travels around the sun, travels over 500 million miles. That's pretty crazy. And that's actually pretty small compared to some of the other planets as it goes around the sun. But that's the total distance for an entire year, right? So that would be if I started at this point and went all the way around, I'm going to travel 584.336 million miles. But I don't want to know all the way around. I just want to know one day. So how can I get 1 day's worth of this distance?
So is that over 365?
Exactly. So in 1 day, we're going to take that 2 pi r and divide it by 365, right? So 2 pi times 93 divided by 365, which is whatever that number was I just had, divided by 365. So let's see what my trusty calculator tells me there. That's 1.6009 and stuff. And they told us to round this to the nearest tenth, to 1 decimal place. So it's 1.6 million miles in 1 day.
All right, thank you.
Yeah, you're welcome. Now think about that. So in 1 day, so if we start at the stopwatch right now, and we come back at 11:15 tomorrow morning, the Earth will have traveled around 1.6 million miles as it's cruising around the sun. That's an insanely large number. But the universe is a big place. And that's nothing. That's actually nothing, because you think about the sun actually orbits around the galactic central point, the center of the Milky Way galaxy, and it moves a lot faster than that. So, and we're moving with the sun and all that. So if you look at our speed relative to the galaxy, it's insanely high. But that's for an astrophysics class, not for a trig class. But you can see how even just, remember what we're supposed to be studying here? Supposed to be studying triangles, right? Here's an example of something that has nothing to do with triangles, and yet it's very trig related. So. All right, well, anyway, so there you go, Diego, for number 13. All right, are we good? Sounds like we're kind of running out of steam. All right, so I'm going to hop up to the whiteboard. I will be back with you guys in just 1 second. Okay, so last time we defined the 6 trig functions. So let me just remind you what those were and how we define them. They were all defined in terms of a right triangle. So I'm going to draw a right triangle here with the angle that we're interested in. Call that theta. But I'm going to set it up just as if theta was in standard position. So we'll just look at, say, this right triangle right here. And we labeled the three sides: opposite, adjacent, and hypotenuse. Right? So opposite, adjacent, hypotenuse. And so we defined them this way. So the sine of theta was the opposite divided by the hypotenuse. The cosine was the adjacent divided by the hypotenuse. The tangent was opposite over adjacent. And then the other three, we had cotangent was the adjacent over the opposite. Secant was the hypotenuse over the adjacent. And cosecant was adjacent over the opposite. So this is how the ancient Greeks defined them. They just went, hey, we're going to look at the ratios of the sides. We're going to give them names. Here they are. Okay, so again, very, very old definition. But we saw some relationships between them that were kind of big, right? The first, and this was when I first asked if people saw, actually, I don't even think I brought this up. I think somebody in class, I forget who it was, said, well, aren't those just like the reciprocals? And you'll notice that these three, the cotangent, secant, and cosecant, they're just the reciprocals of sine, cosine, and tangent, right? Cotangent and tangent are reciprocals, secant and cosine, sine and cosecant. So that means you really only need to know the big three. You know these three, sine, cosine, tangent, you got the others. You just got to flip them over. All right, so we got here. We defined it, and it was actually pretty easy. Given a triangle, you just take the three sides, and you can find their values. And in fact, we did a couple of special angles. Let me remind you about one of those. Like, let's look at pi over 4. So when we did the angle pi over 4, also known as 45 degrees, this was the one that came from this triangle, the one that was half of a square. So we had 1, 1, and root 2. And so from this, we found, for example, that the sine of pi over 4 was 1 over root 2. So was the cosine. The tangent was 1, because opposite over adjacent was 1 over 1. And then the other three were just the reciprocals of these. So if you were to take those three and flip them over, 1 over root 2 flipped over is root 2. That was the cosecant. Cosine flipped over is the secant. Tangent flipped over, well, 1 when it flipped over is just 1. But that was the cotangent. So if you know the lengths of the sides, no problem. Just do the right ratios and you're good to go. All right, so that's where we were last time. Hopefully everybody's kind of on board and we're ready to push forward. Because now here's my question. Like, this is awesome, by the way, this whole like SOHCAHTOA thing. This thing is awesome if our angle fits in a right triangle. Right? I mean, if it's in the right triangle, we just take the sides and we're good to go. So what about this? What if I were to ask you, what's the, say, sine of 100 degrees? Now, 120 degrees is a perfectly fine angle. It's actually part of triangles, right? Think about triangles. You know that the sum of the angles can't be more than 180. So we could definitely have 120 degrees. But the problem is it doesn't fit in a right triangle. As soon as we use 90 degrees for that right angle, we're restricted to at most 90 degrees for the other two. All right, well, I still want to be able to get the sine of 120 degrees. And this isn't just for the hell of it mathiness. No, this is for actual application. We get angles 120 degrees all the time. So the question is, can we redefine the trig functions so that we're not stuck to right triangles? Right, and this is really the issue. These 6 definitions with the side lengths, these are fine as long as our angles are between 0 and 90 degrees. Or in radians, 0 and pi over 2. Now, to a mathematician, oh, I don't like this. I don't like this at all. Because remember how mathematicians, like I've told you a few things about it, we're lazy. We're not creative. We name everything exactly as they are. Well, we're also sore losers. We don't like being told you can't do something. Right? A great example of that is I. Remember I, square root of negative 1? That totally was a mathematician being a butthurt loser. Someone goes, oh, you can't get the square root of negative 1. Oh yeah, watch me. I'm gonna call it I. And next thing you know, we have complex numbers which end up being useful in lots of situations. Okay, well, yeah. So mathematicians run into this and go, okay, well, this is great if I'm between 0 and 90 degrees, but I want more. I want more. I want to be able to do this for any angle. Don't restrict me to a right triangle. Okay, well, here's how we're going to do it. Here's how we're going to do it. We're actually going to turn our attention away from triangles for a second, and we're going to look at what's called the unit circle. All right, so unit circle. So it's a circle, duh. What the unit means, unit just means radius 1. So we're going to look at a circle whose radius is 1, and we're going to center it at the origin. So here are our axes. We're going to make a circle centered at the origin of radius 1. So that means that this point is the point 1, 0. This is the point 0, 1, and so on. So negative 1, 0, and 0, negative 1. So when we talk about the unit circle, this is what we mean. Circle of radius 1 centered at the origin. Now, suppose that we have an angle in here in standard position. Okay, so this is our theta. What we're going to do is we're going to make a right triangle out of this. So if we're in the first quadrant, that's an angle between 0 and 90 degrees, or 0 and pi over 2 radians. It's in the right triangle. There's our right triangle. Now, let's think about how we're going to get the trig functions from this. If we go back to our definitions, we need to know the 3 side lengths. We need to know the opposite side length, the adjacent side length, and the hypotenuse. All right, well, the fact that it's a unit circle tells me that the hypotenuse is 1, because that long side is the radius of the circle. So that one's just length 1. Now, the other 2 sides, horizontal and vertical sides, those are actually the x and y coordinates of the point that's on the unit circle, where that terminal side passes through. right? So you look at that terminal side, it goes through that point X and Y. Well, those coordinates give us the other two sides of the triangle. I mean, that's just how the coordinate plane works. All right, well, let's see what that does to the sine, cosine, tangent, cotangent, secant, and cosecant. Let's look at what those are going to be defined as if we're on the unit circle. So we'll start here. We've got sine. Well, the sine of theta that's going to equal the opposite side, which is y, divided by the hypotenuse, which is 1. So sine of theta is equal to y. Okay, yay, that's its definition there. So cosine do the same thing. The adjacent side is x, the hypotenuse is 1, so we get x divided by 1, which is x. If we go to tangent, opposite over adjacent is y over x. All right, well, the other three are just the flip of these. So cotangent is x over y. Secant is 1 over x. And cosecant is 1 over y. So we're still using the whole SOHCAHTOA business. We're just looking at it with these lengths on the unit circle. All right, so here's what mathematicians did. They said, well, clearly that's how this works in the first quadrant. So then how about this is how it works always? So it doesn't matter where your terminal side is. All you need to know is what point on the unit circle does it intersect. That point gives us the x and y coordinates that we can then put into these formulas to get our trig functions for angles that are not in the first quadrant. Okay, so these are the ones you want to know. They are so much more valuable than SOHCAHTOA. I know you're more comfortable with the opposite, hypotenuse, all that kind of stuff, because that's how you were introduced to trig functions. And you probably saw that before this class. And that's awesome. I mean, it is. That's a great way of remembering it, but it's got major limitations. Those limitations are, we're stuck with our angle values, only between 0 and pi over 2, between 0 and 90 degrees. This definition lets you do it for any angle whatsoever. You can go ahead and evaluate the trig functions. All right, so it basically just extends it to more than just first quadrant. All right, but the goal, the important thing is always going to be finding that point. What is the point where we intersect the graph of the unit circle? Because its coordinates are going to give us the 6 trig functions. And that question is not always so easy to do, right? Or it's not so easy to answer. What is that point of intersection? For nice angles, it will be easy. But for non-nice angles, it's going to be a little challenging. All right, but this actually lets us do some calculation, find some values for these trig functions, even if we're not in a right triangle. So we're actually going to do a pretty easy one. Let's look at 90 degrees. Okay, 90 degrees, also known as pi over 2 radians. And let's find the trig function values for 90 degrees. All right, so here's what we want. I want to know What is the sine of 90 degrees? What is the cosine of 90 degrees? What's the tangent, the cotangent, the secant, and the cosecant? And I'm only doing 90 degrees because that's the first angle that we run into that's a problem when it comes into right triangles. You can't have a second 90-degree angle in a right triangle. Because if you have two 90-degree angles, there are no degrees left. You don't even get a triangle. But I still want to be able to get these values. So here's what we're going to do. Let's look at the unit circle. And let's think about an angle of 90 degrees and where that terminal side happens to be. So if I were to rotate 90 degrees, that's a quarter rotation, and now I'm straight up. Right, so there's my 90-degree angle. So what I need to know is what is the point where I intersect the unit circle with my terminal side? Okay, well, it's that point, which is 0, 1. And so now let's get our sine, cosine, and so on. So the sine is the y-coordinate. The y-coordinate of that point is 1. So the sine of 90 degrees is actually 1. Okay, cool. That's the sine of 90 degrees. The cosine of 90 degrees is the x-coordinate. The x-coordinate of this point is 0. So the cosine of 90 degrees is 0. Like, it literally is that easy. If you know the point, all right, x-coordinate is the cosine, y-coordinate's the sine. All right, so that's those two. And notice that we couldn't have done this with opposite over adjacent, or hypotenuse and adjacent over hypotenuse, because there was no triangle. All right, so now what about tangent? So tangent is going to be the y-coordinate divided by the x-coordinate. So that's going to be 1 divided by 0. And that should have just made you a little bit upset. Or at least the alarm bell should have gone off. Because dividing by 0 doesn't work. You can't do it. It's impossible to divide by 0. So it turns out that this one is undefined. There's actually no such thing as the tangent of 90 degrees. All right, now if that starts making you unsure, and you might start thinking, okay, well, now there's clearly a problem with how we define this. It's actually okay for functions not to be defined. Happens all the time. Think about the function square root of x. Are there things that you can't plug into the square root of x? Well, if we want real values, then yeah, like we can't plug in any negatives. Or same thing, like natural log of x. Are there numbers you can't plug in? Yeah. Can't plug in 0, can't plug in anything less than 0. So you've seen in your math history lots of examples of functions that are not defined certain places. Well, it turns out tangents is going to be another one. There are certain places where it's undefined. All right, well then what about cotangent? Well, cotangent, if we flip those over, x over y is 0 over 1. And that's actually totally fine. 0 divided by 1 is actually 0. So while tangent may not be defined, cotangent is. The cotangent of 90 degrees is actually just 0. All right, well, let's finish these off. So secant is 1 over x. So that's 1 over 0. Oh, that's another one that's undefined. All right, so I guess both tangent and secant don't work here. Cosecant is 1 over y. Well, the y was 1. 1 over 1 is 1. So hopefully you're seeing how quick it can be given the coordinates. You just put the coordinates into these formulas and see what you get. But I also like this angle because it shows you that not all of them work all the time. And we're going to see this. There are plenty of times where certain of these functions is undefined. There are going to be ones that just don't work for certain angles. Well, I mean, it's good to know. It's good to know where things aren't actually defined. But this was actually huge when mathematicians made this step and just went, all right, let's do the same thing, but let's look at it as just the points on the unit circle. This is all you got to do, right? But it's really important that you remember we're on the unit circle. It only works, these definitions only work when we're on the unit circle. If we've got a bigger circle or a smaller circle, the points that we get won't give us these things as our definitions. We're going to have to scale them appropriately, and I'll show you that later. Okay, so here's what we're going to do. We are going to start figuring out the trig function values for nice angles. We're going to start making a list of all kinds of different angles that we know and what their corresponding trig function values are. All right. Now, to help us do that, I'm actually going to share with you a little bit of a chart that we're going to fill out. So let me hop to my computer. I'm going to hit share. You can find this on the Canvas page. All right, if you go to the Canvas page, you'll see this chart. And you'll see that I've got it named. It's called the trigonometric function values for quote unquote special angles. So like I said, if you go to Canvas, on the side, you got a little menu that has a whole bunch of different things on it. And one of them says files. If you click on the files list, it'll give you a list of all kinds of files. And right now, I think the only ones that you'll see there are the syllabus and this. Okay, but it's just a PDF. You can go ahead and pop up this PDF, but we're going to fill this out. We're going to find trig function values for a whole bunch of special angles. And in fact, the numbers that we just found, we've actually done one of these rows, because 90 degrees is going to be one of our angles. All right, so we're going to start filling this thing out. Okay, in order to do this, in order for this chart to work out the way that you're going to want it to work out, we have to be really careful with how we define the different rows. So let me start kind of filling these in and showing you how we're going to do this. All right, so the first row is going to be 0 degrees. So I'm going to go ahead and put a 0 degrees here in our first row. Real quickly, let's convert that to radians. How many radians is 0 degrees?
Zero?
Yep, it's also 0, because think about how we convert, right? We take 0 and we multiply it by pi over 180. Well, 0 times anything is 0. So that's going to be our first number of degrees. Now, the next ones are going to be 30 degrees, 45 degrees, 60 degrees, and 90 degrees. So the 30, 45, and 60, those were the special angles that we saw last time. So we'll refresh our memory about those. But we're going to have 30, 45, 60, and 90 degrees. So let's take care of the 90 degrees real quick. In terms of the sine, cosine, tangent, and all that, we just saw that the sine was 1, cosine was 0, the tangent was undefined, so I'm going to write here UND for undefined. Cotangent was 0. Secant was also undefined, and the cosecant was 1. So that's what we're going to write across this row. All right, so the 90 degrees, let's convert that to radians. How many radians is 90 degrees?
Pi over 2.
Beautiful, pi over 2. Yeah, except maybe let me try writing that so it actually looks like a pi instead of an 11 that's getting crossed out. Sorry about that. All right, so pi over 2. All right, so that's how we're going to do this. That's what these are going to look like. We're just going to continue to fill in all these rows. All right, so let's go ahead and take care of the 30, 45, and 60 because we did these last time. All right, so when I go and I put all these numbers in here, if you are wondering where they come from, I'm going to reference back to the last class. Go watch that video and you'll see where they come from. It's from looking at the right triangles that hold those angles. But first, let me get the radians in here. 30 degrees is pi over 6 radians. 45 degrees was pi over 4. And 60 degrees was pi over 3. All right, so those were the radians. So now in terms of sine, cosine, tangent, and all those. The first one we did was 45 degrees. And we saw that the sine was root 2 over 2. Oops, hold on a second. I apologize. Trying to use my stylus and everything is not so easy when I have a target box. So square root of 2 over 2. And cosine was the same. At least that's in their rationalized form. When we set it up with our triangles, it was 1 over root 2. But I'm in the habit of always rationalizing. Then we saw that the tangent was 1. So then when we flip them all over, cotangent was also 1, secant was root 2, and cosecant was root 2. So that was the first one we did. Then I think we went to 60 degrees. And we saw that the sine of that was the square root of 3 over 2. The cosine was 1/2. Tangent was square root of 3. So then we just flip all those things. Cotangent becomes 1 over root 3, which is the same as root 3 over 3. Secant is the reciprocal of 1/2, which is 2. And then cosecant is 2 over root 3, which when rationalized becomes 2 root 3 over 3. All right, so we developed that. And then we got the 30 degrees just by recognizing that the co-functions swap. So the sine of 30 was the same as the cosine of 60. The cosine of 30 was the same as the sine of 60, and so on and so forth. So this was another pattern that we saw by their definitions, that the co-functions swap. All right, so really all we've done with this chart is we've brought all the information from last time and so far today and kind of put it all in one place. Okay, so the only thing that's actually new on this chart was this row with the 90 degrees that we just did. All right, so let's go ahead and take care of the 0. Let's take care of 0 radians, just so that this is now complete for the first few angles. All right, well, 0 degrees or 0 radians, we can approach this one of two ways. Let me stop sharing here for a second so I can chat with you guys. So we can do this in one of two ways. One, we can just think about the point on the unit circle where the terminal side for 0 radians is located. All right, well, 0 radians means we don't rotate anywhere, which means our terminal side is the same as our initial side, which brings us to that point 1, 0. And we could just go through the same kind of definitions, right? So if we go to 0, it would look like this. So the sign of 0, it's the y coordinate of this point, which is 0. The cosine of 0, it's the x coordinate, which is 1. Tangent is y divided by x. 0 divided by 1 is 0. Cotangent is x divided by y, which is 1 divided by 0, which means that's undefined. Secant. Somehow my zeros turned into thetas. Sorry about that. Secant of 0 is going to be 1 over x. The x coordinate was 1. 1. And then cosecant of 0 is 1 over the y, which is 1 over 0, which is also undefined. Okay, so like I said, that's one way we could have done it. And it worked out totally fine. We have our numbers. As we go across our row, it's going to be 0, 1, 0, undefined, 1, undefined. Okay, well, there was another way that we could have done this. And that is thinking about the co-function identities. Because 0 is going to be the same relationship with 90 degrees, since 0 and 90 add up to 90. So what we could have done is just taken the 90 row and swapped the co-function pairs. Okay, well, either way, what that's going to look like once we, let me bring that back up again. Bring the chart. So here's what we got. If you just look at those numbers we found for sine, the 0, we got 0, cosine was 1. Tangent, 0, cotangent, undefined. Secant, 1, cosecant, undefined. All right, so that's what we got when we just used the point. But like I said, we also could have used the co-function pair swap. Look at these, 1 and undefined for secant, cosecant. If you look at 90, it was undefined and 1. 90, tangent, undefined, cotangent, 0. Swap them for 0. Sine and cosine, 0 and 1 for 0, 1 and 0 for 90. So that co-function property is a huge one. Oh my God, it's a huge one. It means you don't actually have to learn sine and cosine. If you just know sine, all right, you know the sine values, you just do the cosine values in the other way, right? I mean, check it out. Let me turn off the draw so I don't actually write on here because I don't want to. But if you look at the sine column, 0, 1/2, root 2 over 2, root 3 over 2, 1. The cosine column, it's the same things, but backwards, right? This one you go down 0 to 1. This one you go up 0 to 1. Tangent, go down from 0 to undefined. Cotangent, go up from 0 to undefined. Secant, go down from 1 to undefined. Cosecant, 1 and up to undefined. So it means that that's half that we don't even have to remember. So think about this right now. In terms of what we actually need to know in order to draw or to get all these values, let me just show you what you need to know. If you know these, and you know these, so just the sine column and the tangent column, you can actually get all the rest. Let me walk you through that. So if you know sine, you get cosine just by going the opposite direction. All right, so we know tangent, we get cotangent by going the opposite direction. And then you might be saying, but Bruce, how come you didn't tell us secant so that we could just do the opposite direction of cosecant? Well, because you don't need to know secant. You can get secant by flipping over the cosines. You can get cosecant by flipping over the sines. So here's what I would do. If I know my sine, I flip them over, right? The 1/2 becomes a 2. The root 2 over 2 is the same as root 2, and so on. 1 flipped over is 1, 0 flipped over is undefined. So I get the cosecant column. And then once I know the cosecant, I can do them in the opposite order to get secant. Okay, so if you're anything like me, I suck at memorizing stuff. I actually do. It probably doesn't seem like it because you ask me these things and I can just rattle them off. Well, that's only because I've been exposed to them like for literally over 30 years. That's how long I've known about the trig functions. I think I'm probably going on about 34 years of knowing the trig functions. So that's a long time. And because of that, yeah, now I just know them. But to memorize them was horrible. So instead of memorizing like this entire chart, I just remembered pieces of it and then the relationships to build the rest. So that's what I'm trying to share here. So it doesn't feel quite so daunting, especially once we fill this whole thing out. Because, I mean, you haven't even seen how many rows there are. You see that there are some more blank rows. Well, we're like a fourth of the way done with this chart. There's that much more left to go. But it turns out you don't have to memorize all of it as long as you see the pattern. All right, so yay. We now have these values for all these angles. But there clearly are many more angles to get. So let's start banging those guys out. So I'm actually going to have a seat because this is a little bit hard for me to do while standing. So I'm going to have a seat because really the important thing is watching the chart. And if I need to draw something for you, I'll pull up the whiteboard. All right. So I'm just going to switch my camera view here and my speaker. All right. So I'll be right back with you in a second. All right. So I'm actually back with you here, back at my computer. So I'm going to go ahead and turn that on. But let's go ahead and work on getting the rest of these angles, the rest of these special angles. So if you're playing along at home, if you've got this printed out and you're working on filling it out, here's what we need to do. We need to be really careful with where we put our next entries. All right, so let me get back to the color we were in. I think that was the color we were on. So what I'm going to do is I'm going to skip 3. Okay, so there's going to be a blank, blank, blank. And then I'm going to put here 180 degrees. So after the 90, blank, 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 180. And then we're going to go blank, 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 and put 270. And then we're going to go blank, blank, blank. And in the bottom, we're going to put 360. All right. So I want to hit these angles first because these are a little bit easier for us to calculate. Because the points where the terminal side intersect the unit circle are much easier to find the coordinates for. All right, so in terms of radians, 180 is pi. Remember our conversion, 180 degrees equals pi radian. 270 is 3/2 pi, so 3 pi over 2. And then 360, we know that that's the same as 2 pi. All right, so this is what we're going for. Let me jump over to a whiteboard real quick and let's draw a unit circle. So we're going to use this unit circle to reference all the time. All right, so here's our unit circle. And so let's look at an angle of pi, right, or 180 degrees. So an angle of pi means we're halfway, which means our terminal side intersects at this point right here. And I had that up on the whiteboard, the physical whiteboard. I don't know if you remember what it is, but it's pretty easy to get those points. The coordinates of that point, I should say. The coordinates are -1, 0. Obviously, the y is 0 because we are not going up and down. And then the x is -1. Okay, so let's use that point and let's fill in the rest of this. So I'm going to just on the side here, I'm going to write the coordinates of that point. That way we don't have to go bouncing back and forth between the pictures, but that was our or the coordinates of our point. Okay, so let's kind of come back up here so we can see everything again. So sine, the sine was the y coordinate. So that's going to be 0. The cosine is the x coordinate, which was -1. Tangent, y divided by x. 0 divided by -1 is 0. Cotangent, x divided by y. Well, -1 divided by 0 is undefined. Secant is 1 over x. 1 over -1 is -1. And cosecant, -1 divided by 0 is undefined. All right, so there you go. There was the real quick 180 degrees or pi radians. So hopefully you're convinced that this actually is quick once we know the point. If we know the point, boom, just go. Do it. Rattle them out, just use the formulas. Okay, well, what about the 270? Well, 270, 3 pi over 2, that's going to be down here. Let's look at this, 270 degrees, that's this point. And the coordinates on that point are 0, -1. Okay, so let me just reference that over here. This was 0, -1. So if we do the same thing, sine is the y coordinate, -1. Cosine is the x, 0. Y over x, undefined. X over y, 0. 1 over x, undefined. 1 over y, -1. All right, so there are the values for 270 and 180 degrees. Now, before we move on, I just want to draw your attention to something. In fact, let's highlight this. Let's highlight the values for 180. For some reason it's not letting me highlight. All right, well, we'll draw it then. We'll circle this in yellow. Okay, so look at these values. And compare them to the values for 0. Notice that they're almost identical. The only difference is that those ones are now negative ones, right? 0, 0, 1 minus 1, 0, 0, undefined, undefined, 1 minus 1, undefined, undefined. So there are some similarities between 0 and pi when it comes to the trig function values. It shouldn't surprise you the way that they were defined with the unit circle, because the thing about the 2 points at 0 and 180 degrees is they're opposite sides of the circle. They've got the same y, and the x's just are different signs. Well, similarly, let's look at, let's do purple for these. Look at the ones we just found for 3 pi over 2, 270 degrees, and the one for 90 degrees. And exactly the same thing happened. The only difference is that the ones are now minus ones. Well, if you think about those two angles, those are the top and bottom of the circle. So just like the points that were on the sides, the points that are on the top have some symmetry, and therefore their trig function values are similar. All right, so I was going to say interesting. I don't know that you guys find it interesting, but at least it's a pattern, and it's a pattern that can be useful to help us remember what's going on. Okay, well, let's jump down here and take care of 360 degrees, also known as 2 pi. But if we go 2 pi, we're back to where we started. So it's going to be really easy. Remember this row for 0? It's going to be exactly the same for 360 because they are coterminal angles. This is the other reason we actually care about coterminal. We mentioned that before. Remember, coterminal just means they are angles who share a terminal side. And at the time, you may have thought, okay, yay, we call them that, big deal. Why do we care? Well, this is why we care. Because if coterminal angles share the same terminal side, that means they both share the same point on the unit circle, which means they share the trig function values. So if you're given some angle, and maybe it's an angle you don't know, if it's at least coterminal to one you know, that's good enough. Because trig function values of coterminal angles are identical. All right, well, there you go. We're over halfway done now in terms of filling in this chart, right? We've got almost everything, but we got a couple more that we definitely need to fill in. And these are going to be the angles that are in the other quadrants that are not in quadrant 1, but are related to the ones in quadrant 1. All right, so I'm going to go back to my whiteboard, but actually before I do that, because it's been a while since I checked in, I've been talking a lot. How are we doing at this point? If you're feeling pretty good about this, why don't you give me a thumbs up in your window? You guys know about that in the reactions, you can give a thumbs up. Or give me a like all good in the chat or something like that. If you have a question and you're a little bit uncertain about asking, how about you give me the hand raise reaction?
So I had a quick question. We didn't on the homework assignments, we didn't get a lot of, finding tangent, secant, cosecant. I think there was like one question that I got in both assignments, but on the exam on Wednesday, are we going to be just doing these for part of it?
Okay, so I think there are two parts to this question for you, Catherine. So first of all, yeah, you probably haven't run into a lot of other trig functions yet because it's still kind of early on. In terms of, are you going to have to be able to do them on the quiz on Wednesday? Yes, but only if I give you a right triangle. Okay, so the only kind of trig anything I'm going to ask is going to be about right triangles on the quiz. So the stuff we're talking about today, that'll be for actually the first exam. I think it will cover, and you'll get a lot of practice on this stuff in section 7.3 and 7.4. 7.3 is specifically just about sine and cosine. 7.4 is about the others. I teach it to you all at the same time. So you won't see crazy angles or have to have this kind of stuff memorized or anything yet, especially not for the quiz on Thursday. So did I answer that?
Yeah.
Okay, good. Okay. All right, so it looks like we're feeling pretty good so far. So let's go tackle some of these other angles. All right, so here's what we're going to do. We're actually not going to fill out our chart in order. We're going to fill out our chart kind of jumping around. But here's what I want to do next. So here's our unit circle. I want to look at the angles that have symmetry with 45 degrees. Okay, so this is 45 degrees or pi over 4 radians. Because this one, we do know the coordinates for. The coordinates are √2/2. And I know some of you might be going, but Bruce, how do we know that? You assert that we know that. How is it that we actually know that? Can somebody answer that question? How do I know for absolute certainty that that point is √2/2, √2/2?
The chart.
Okay, yeah. I mean, we've got our chart and we know the sine and cosine were √2/2. And we know the sine and cosine are the y and x coordinates. So yeah, I mean, we developed this last time. We know the sine and cosine of 45 degrees, which means we know the y and the x. Okay, so here are the other angles that I'm interested in. I'm interested in the other angles that bring me to these points, √2/2 minus √2/2. The one over here, and pardon my picture for not being symmetric exactly, but this will be minus √2/2 minus √2/2. And then the one over here that's minus √2/2, √2/2. So I'm basically just taking the points that are symmetric to this one in the other quadrants. So that means I want to know what are the other angles that do this. All right, well, it's probably not hard to tell from the symmetry that they're all going to be related to pi over 4 or 45 degrees. So the one that's in the second quadrant, this is 135 degrees. The one in the third quadrant is 225, oh, not 222, 225, sorry about that. 225 degrees. And then the one that's down here, that's 315. degrees. So those are the ones that we're going to now fill in. And the reason I'm picking these is because they're going to be really fast. I already know all the coordinates, which means I can do all my trig definitions and get them pretty quickly. All right, so let's go put those in the chart. Now, when we put these in the chart, they have to go in very specific places. Make sure I'm drawing with the right color. They are going to go right here, 135 degrees. So it's going to be 90 blank, 135 blank, 180. Another blank, 225, then 270, then another blank, then 315. So those are all the points that have the symmetry with 45 degrees. So if you convert those to radians, that's 3 pi over 4, 5 pi over 4, and 7 pi over 4. You can either trust me or you can do it on your own. And you'll see that those are the radian equivalents, those degrees. All right, so now let's think about the coordinates on these. Let me just remind you that for 135 degrees, those were minus root 2 over 2 and root 2 over 2. All right, so here we go. So the sine is the y, root 2 over 2. Cosine is the x, minus root 2 over 2. Tangent was the y divided by the x. Well, I divide the same numbers, I get 1. They're different signs though, so it's actually -1. Cotangent, well, it's just the flip of that. Secant is 1 over the x. Well, if I flip that over, I get minus root 2. And cosecant is root 2. It's 1 over y. So there are the values for 3 pi over 4. Well, before we stray off of this, let me just show you. All right, so there's that row we just did. Compare that to the row for pi over 4, 45 degrees. Ah, darn it. Hold on a second. That's not the one we just did. This is the one we just did. All right, so compare this row to the row for 45 degrees, and you'll see that everything is the same except for the sign has changed on some of them, right? The sign has changed on these 4. All right, that's not coincidence. That's because we have the same points, just the signs have changed on some of the coordinates. Well, because of that, check out what we can do for 225. 225 degrees, I know, is going to be plus or minus these values. So I'm just going to write them all as positives. But now the question is, which of them are actually negative? Well, that point, you look at that one, it was in the 3rd quadrant. Both the x and y are negative. So that means sine and cosine are negative. It means secant and cosecant are negative because those are just reciprocals. Right? If I flip them over, I don't change the sign. And then tangent and cotangent are positive because I'm taking a negative divided by a negative. So again, this row, exact same values as 3 pi over 4 and pi over 4. They just have different signs, plus or minus signs, depending upon which trig function. All right, well, that's going to make 7 pi over 4 really fast as well. So let's do again, root 2 over 2, root 2 over 2, 1, 1, root 2, root 2. We know we're going to need to make some of them positive and some of them negative. Well, if we go back to the coordinates of that point, we had a positive x and a negative y. So sine is going to be negative, cosine is positive. So secant is positive, cosecant is negative. And then tangent is a negative divided by a positive, so that's negative. And the same with cotangent. All right, so knowing pi over 4, knowing 45 degrees, means that we know these other ones, just with the exception of plus or minus signs, and we can take care of that just by looking at the coordinates on the point. All right, so, man, yeah, this chart's almost done. There's more to do, and of course, those are going to come from similar idea with 30 and 60 degrees. But I want to put in a little plug for radians real quick. I know you guys still don't like radians. You don't care for radians. They're confusing. They don't really make sense. If I say an angle like 5 pi over 6, you're like, I have no idea what that means. Well, let me just put a little plug in here for radians, because I want you to look at the radian values for the 4 that we just did. Right, the ones that were all symmetric to each other. So we had pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Do you notice a pattern here? I hope. Notice that they're all fourths, and it's just odds on top, 1, 3, 5, 7. So anytime you get an angle in radians that reduces to a number of fourths, you know that it's going to have trig values that are like pi over 4. They're just going to be off by plus or minus signs. It's a hell of a lot easier than looking for the pattern of 45, 135, 225, 315. I mean, there's a pattern there too. You're adding 90 degrees every time. But it's a little bit harder to actually look at an angle and go in degrees and go, oh yeah, that's related to 45 degrees. Because you have to subtract off multiples of 90, where in radians, you're just looking for fourths and you're done. Look, I try to give you all kinds of positive things about radians, because otherwise you're just gonna be like, yeah, screw it, who cares? And trust me, it's in your best interest if later you think radians. So I'll do my best to get you there. All right, so we're almost there. Let's finish out this chart. Obviously, what we're going to need to do is find the point for 30 degrees and 60 degrees and kind of do the same thing where we use symmetric points. So let me draw another one over here. We'll start fresh. The unit circle. All right, so here's our unit circle. That is definitely not a circle. And let's go to 30 degrees. So 30 degrees was over here. And as radians, that was pi over 6. Again, we know the coordinates of this point, because if you go to the chart for 30 degrees, you can see that we found that the sine was 1/2 and the cosine was √3 over 2. So that means that the coordinates of the point on the unit circle are √3 over 2, 1/2. All right, so there's that one. Now, we want to get the other symmetric points, which are going to be these guys. So the question is, what are those angles? That are going to give us the symmetric points. The only difference again, plus or minuses. All right, now these might be a little bit harder to find than the ones that were for 45 degrees because we just had to go around a quarter turn each time. So adding 90 degrees was not a big deal. It turns out that this one is 150 degrees. And the way to see that is if we think about the 30 degrees as how far we have to go from the x-axis to get there, notice that that is as this angle right here. So we're 30 degrees shy of making it halfway around. Halfway would be 180. You can subtract your 30. Similarly, this one, notice that it's 30 degrees more than halfway. So if halfway is 180 and we add 30, that's actually 210 degrees. And then by a similar argument, you can see that this is 330. It's 30 degrees shy of making it all the way to 360. And this is where, if you're like me, all you see here is an X-Wing fighter from Star Wars. I can't help but see an X-Wing fighter when I draw that picture. I'm a big Star Wars nerd, in addition to being a baseball nerd, as I'm sure you noticed from my shirt today. If you didn't go back and watch the video, you'll see why. All right, well, there are numbers, 150, 210, and 330. So let's go put those into our chart. I need to make sure I'm drawing the right color. I'm not. Okay, so where those are going to go, the 150 is going to go in the spot between 135 and 180. The 210 is going to go in the next blank. And we're going to skip a bit. And we're going to skip all the way down to the last empty row, which is 330. So you'll notice that in this chart, we're just going from smaller to bigger. Right? It's just because of the symmetry, that's where these guys pop up. All right, now if you convert these to radians, 150 is the same as 5 pi over 6. 210 is 7 pi over 6. And then 330 is 11 pi over 6. All right, well, we're going to do the same thing that we just did, where we're going to use 30-degree numbers. And the only thing we have to do is potentially change the signs on them, the plus or minus signs. So to help us with this, I'm just going to copy them down real quick. So we're going to get 1/2 root 3 over 2, root 3 over 3, root 3, 2 root 3 over 3, 2. And I'm just going to go ahead and do that for all of these, leaving a space for potentially some minus signs out front, because I know that's the only thing that might change. All right. So now let's take care of pluses and minuses. So let me just go ahead and remind you what the coordinates of these points were. For the 150 degrees, the 5 pi over 6, the coordinates on this point were negative root 3 over 2, comma 1/2. For the 210, it was negative root 3 over 2, negative 1/2. And for the 330, it was positive root 3 over 2, negative 1/2. All right, so let's change all the signs. So sine is 1/2, which means it's positive. Cosine, negative √3/2. Tangent and cotangent, both negatives, because it's positive divided by a negative. Secant, the x coordinate, so that makes that negative. And cosecant is 1/y, so that's positive. If we go to 210, both the x and y are negative. So sine and cosine are both negative, which means both secant and cosecant are negative. Tangent and cotangent, since I'm dividing the y by the x or vice versa, negative over negative is positive. Those guys stay the same. When I jump down to the last one, the y coordinate is now negative. So sine is negative, cosine is positive. So that means secant is positive and cosecant is negative. And then tangent and cotangent, since they're one divided by the other, positive divided by a negative is negative. All right, so fast. Now that we're starting to see patterns, this is speeding up. And another quick plug for radians. Take a look at the radian values for these angles that we just did. They were pi/6, 5 pi/6, 7 pi/6, 11 pi/6. Notice again, each one of them, when we reduce it down, it's got a 6 on the bottom. Well, that's crazy fast and easy pattern to see. Whew. All right, so we're almost there. Let's bang out the last 3. Now, the last 3, we're going to cheat just a little bit. Not really, cheat a little bit. But we know that they're going to be related to 60 degrees. So I'm not going to worry about drawing the points because I know it's just going to be these values. I'm just going to change some signs, plus or minus signs. So why don't we actually go ahead and just fill in all of those values real quick. So this will be √3/2, 1/2, √3, √3/3, 2, and 2√3/3. Again, potentially minus signs. Same thing here. So √3/2, 1/2, √3, √3/3, 2, 2√3/3, and then the same thing in the final one. All right, I'm even going to go ahead and fill in the plus or minuses before we deal with what the angle numbers are. So think about this one. This is going to be the one that's in the second quadrant. In the second quadrant, x is negative. So cosine gets negative, secant gets negative. Y is positive, so sine and cosecant are positive. And then tangent and cotangent are going to be negative because plus divided by minus. All right, this guy, the next blank, is the one in the third quadrant. X and Y are both negative, so negative, 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 negative on the sine, cosine, secant, cosecant. And then tangent and cotangent are going to be plus because we have minus divided by a minus. And then the last one's in the fourth quadrant, so positive x, negative y. So negative y, positive x. So negative sine, positive cosine, which means negative cosecant, positive secant. And then tangent and cotangent are also both negatives. So we didn't even actually have to know what the angle numbers were to figure out what those values are going to be by using the symmetry of the circle. Okay, well, the angle values are 120 degrees for that one, 240 degrees for the third quadrant one, and 300 degrees for the fourth quadrant one. And if you convert those, I'm sure it's going to come as no surprise to you that they end up being thirds. Which again is kind of following the pattern that we saw in the radians. So this is one of the many reasons why I'm very pro radian, why I think radians are the thing you should worry about, because it's really easy to recognize which of the first quadrant angles they're like just by looking at them in reduced form. Whew. Okay, so we have this incredibly large filled out chart that I know looks really, really messy because of everything that I've drawn on here, all the other colors and everything. And also it's my horrible handwriting. But what I'm gonna do is later today, I'm gonna put up a completed form as a PDF and put that up into the Canvas shell so that if you want, you can go ahead and download one of those as well. But I highly recommend you go through the process of filling this chart out. If we were in face-to-face, if we were in the classroom together, I would have handed you one of these and I would have made you fill them out. It's going to help you learn the numbers. It's going to help you see the patterns. It's going to help you kind of like do everything with this. So I highly recommend that you, if you can, print one out and do it on your own. If not, you can do exactly what I just did. You can open up the PDF and you can, you know, just use these little like draw, erase, highlight things. And so you can draw onto PDFs. But I would definitely go through that practice just because it definitely helps. And these are angles that while I can't make you memorize them in the format of class that we have right now, like I can't make you take a test where you don't have notes or anything. While I can't make you memorize them, it's in your best interest to memorize these angles and memorize these values. And as we go, I'm going to give you more tips. I'm going to give you more things to use to help you remember what goes where. Because it turns out, no joke, that really the only thing you need to know, remember how I originally circled these two, the tangent and sine? It turns out the only one you need is the sine. And you only need to know sine from 0 to pi over 2. If you know those values, you can recreate this entire chart very quickly if you know the patterns. We've already talked about some of them, right? The reciprocal nature, the big three versus the other three, the co-functionness, right? So we talked about those patterns, but there are way more patterns that are in this chart that you can use to help you fill it out if all you remember are these 5 numbers. These 5 numbers drive everything else. All right. So while it may seem daunting because you look at this huge chart and you're like, Jesus, Bruce suggests that I memorize that. You know, good luck with that, right? I know what a lot of you are thinking. But it does. It turns out that if you know just those 5 things, you're going to be good to go. All right. So I'm actually going to stop with new stuff here real quick. I know that we definitely have some time left, but we didn't take a break. I just kind of kept going and I apologize a little bit. I kind of got into it and I didn't think about stopping. But if you kind of got worn down, if you stepped away, remember, you can always go back and look at this video, but go back and review the video, watch how it's all built, and make sure you come with questions for next time, because next time I'm going to start showing you patterns. I'm going to start talking about other things that we can see from this chart and things that this tells us about the functions. So think about functions and things like domain and range and all that kind of stuff. Even their graphs, like we can get a lot from this chart. But before we call it a day, I do want to remind you that we do have a quiz next time. It's our first quiz of the quarter. and it's going to be on section 7.1 and 7.2. Okay, so only sections 7.1 and 7.2, the first two sections. And so 7.1, that's the homework that's due tonight. And so you've probably been playing around with it, all the converting angles between radians and degrees, finding arc lengths, finding areas, right? All that good stuff. That's 7.1. 7.2, that's the definition of the trig functions using right triangles, right? So things that you should be able to do from that section for the quiz are, if I give you a right triangle with an angle, you should be able to tell me all the trig functions. Or if I just give you a side and an angle, you should be able to figure out one of the other sides, right? So like think about the applications. Remember I showed you that one about trying to figure out how tall a tree was. And all we need to know is an angle in that triangle and one of the lengths that wasn't the tree, right? So be able to do that kind of stuff. That's going to be more calculator intensive because I don't expect that you know things like the sine of 27 degrees. So make sure you know how to use your calculator. One word of warning there, again, degrees versus radians. Make sure you're in the right mode, okay? So quiz next time on 7.1 and 7.2. The quiz is going to open up at 11 o'clock. Like right now, if you go and you try to click on quiz number 1, it will say something like not available until Thursday at 11. So starting at 11, it will be live. You can then access it, work on it. It needs to be uploaded by 11:40. Okay, so by 11:40, it needs to be uploaded. That's 30 minutes to take the quiz, and then another 10 minutes to deal with whatever shenanigans happen regarding uploading and all that good stuff. All right, so just has to be uploaded by 11:40, and then at 11:40 we're going to meet in here in the Zoom classroom and go forward. Okay, so that's what's happening on Thursday. Wednesday. Also, don't forget to get in and finish the homework tonight by midnight. That is a hard and fast deadline, so don't push it.
What was the scanning app that you used, like to use called?
So the one I use is called Cam Scanner. I'll go ahead and type it in the chat. It's Cam Scanner. That's the one that I do. That it's super easy. You just take pictures and then like say convert to PDF, and it makes a PDF file, and then you can send it. I know that there are a ton of apps out there. Like my sons, neither of my sons actually use Cam Scanner. They use something else. I think that's a generational thing. But there are a bunch out there, but that one I know for sure works. So that might be worth playing around with a little bit. Try.
Essentially, we do it on our phones, right? We take the picture on our phones, the scan, and then we would send it to our laptops and save it, and then it would upload to the computer.
Well, okay, yeah, I guess it depends how you do it. Right? Like if you're accessing everything from your phone, like if you're using a Canvas app or whatever, you don't have to send it to your laptop. But if you use your laptop like I do, then yeah, what I do is like if I worked it out on paper, I would then take a photo with my camera on my phone, use the Cam Scanner app to turn it into PDF, email it to myself, so then I could upload it into Canvas.
Yeah, okay.
Yeah, again, that's why I give you guys lots of time to a lot of extra time with these things to make sure you get them uploaded. If you're having any trouble with the uploads, because it happens, I get it. If in doubt, send me the files, send me your photos as an email, right? Because go ahead and email it to me. And as long as it's pretty close to the time, I'm going to call it good. You know what I mean? Like if the email comes to me at 11:42, I'm not going to penalize you for it. I'm going to still grade it. That email comes to me at 12:30, I'm going to be like, nope, this is late. Right. So, because I get it, stuff happens and weirdness happens. When in doubt, and this isn't just my class, I recommend this for all your classes. When in doubt, if something funky happens, reach out to your teacher. All right. Because We understand we're living in the same world and shit happens for us as well. Okay. But number one is you got to communicate, because if you don't tell me, I don't know. And I'm just going to think, that Catherine, she's just a slacker. She just sent it to me at 12:30 for no reason, when I don't know, oh my God, my internet went down and I couldn't access it, blah, blah, blah. Right. So, but if you let me know, I mean, basically, I'm not a dick. All right. And I understand that life happens. Okay. So, but it's way easier for me. It's less likely something gets lost if it's uploaded through Canvas. Otherwise, emails go out of sight, out of mind. Sometimes I delete them on accident, right? Things like that. So it's in your best interest to upload them through Canvas.
And last question, sorry. We have
Sure,
30 minutes to work how many problems?
It's probably gonna, well, it changes. It depends on the quiz. It's usually 1 page front and back. So 4 or 5,
Okay.
something like that. Time should not be an issue. If time's an issue, it's because you're not prepared for the material. If you know this stuff, if you've been doing the homeworks and coming to class and everything, the time should not be an issue.
Thank you.
Yep, you're welcome. All right, so any other questions before we call it a day? All right, well, with that, I'm going to wish you well on the quiz, and I'll see everybody on Wednesday.